Hi, everyone. Thanks for taking the time to come along to my talk. I'm Shan from the University of Edinburgh. Today, I'd like to introduce a little friend I met on my research journey. It's a miniature electrochemical oxygen sensor, and I'll show you a model I built up for him, and I'll talk through how I validated the model. So let's get started. The oxygen level monitoring has been applied commonly in medical areas. Detecting a dangerous complication after a colorectal surgery is one of the applications. The complication was caused by the failure of oxygenated blood supply. It's called anastomotic leakage. Anastomotic leakage describes a breakup between two reconnected ends. It could cause a high mortality and morbidity. Because of this, we think a localized, real-time, and continuous measurement for the oxygenation would be really helpful. So we developed this miniature implantable oxygen sensor. As you can see here, the photo here is shows a fully assembled oxygen sensor. The oxygen sensor was fabricated by the traditional semiconductor manufacturing processing. A microelectrode array of platinum was fabricated on a silicon wafer. The oxygen is electrochemically reduced on the microelectrode array, and the current, the steady-state reducing current, can be measured and proportionally linked to the partial pressure of oxygen. As you can see here, the good sensitivity and high linearity have been reported previously. In our oxygen sensor, we have two types of different designs. One is a single microelectrode, another one is a 3x3 microelectrode array. The microelectrode array was fabricated for intensifying the current. All of these designs contains the macro disks with 25 micrometers of radius and 200 micrometers of pitch. Because the steady-state reducing current is a diffusion limited current, so we want to build a numerical model in COMSOL 6 to explore the diffusion patterns and the diffusion overlapping effect in our oxygen sensor. This model was built and validated for the single microelectrode first. Then we extend this model to a 3x3 microelectrode array. The photo here shown on the bottom is similar to the result for the single microelectrode. That is an oxygen distribution. As you can see here, we were talking through a lot about diffusion patterns, but what actual diffusion patterns look like in a microelectrode array? Let's have a look together. During a short period of time, they are very small, they are thin diffusion layers, so they are individual small diffusion layers on each microelectrode. With time increasing, they started to become individual radio diffusion layers. At this time, we can measure the highest steady-state reducing current. But as time goes on even further, they start to cancel and merge with each other. That means the current will decrease until they fully overlap with each other across the whole surface of the microelectrode array. And so at this time, the microelectrode array would work as one electrode. We see that from this theory. Now we want to achieve that in our model. We picked a unit cell in our model. The width of this unit cell equals to the center-to-center distance between two adjacent microelectrodes. We took advantage of the rotational symmetry of our microdisks. We simplified this model from a 3D model to a 2D model. As you can see here, the figure B, the orange line in the figure B, is an indicator of the symmetry axis, which is normal to and goes through the center of the microdisk. The green line here describes the surface of the microelectrode. All the parameters here we will measure in a pure water and 25 degrees. For a single microelectrode, the width of the simulation box was set as semi-infinite length first, that is 1,000 micrometers. So for the oxygen diffusion coefficient in a pure water at 25 degrees, that is 2 times 10 to minus 9 meters squared per second. For the oxygen concentration, we use that as an initial condition and a bulk boundary condition, that is 0.25 molar per meter cubic. As for the reaction rate, because we assumed there is no other reaction happening in the analyte which could affect the diffusion of oxygen, so we set it as 0. For the surface concentration, because we think the oxygen reduction is a rapidly kinetic reaction, That means after the simulation starts, all the oxygen will be consumed directly, so there's no oxygen accumulating on the surface of the microelectrode. We set that as 0 as well. The simulation was run from 10 to minus 6 seconds to 600 seconds, with 10 time steps per decade. The simulated result was compared with the Schmüser equation first. Schmüser equation was doing the theoretic and mesh refinement checking. Schmüser equation describes a diffusion limited response to a step potential over whole time range around 0.6% of your accuracy. After we compared that theoretically, we validated our model to comparing with our experimental result. Because of the application of our oxygen sensor, so we are mainly interested in the steady state time range, which is from 10 seconds to 100 seconds. So everything is ready. Let's run the simulation. As you can see here, the blue line is an experimental result to single microelectrode, and the orange line here is a simulated result to single microelectrode. There is a big difference between each other, and I was wondering where the differences from. Let's go back to have a look of all the parameters we were using. The oxygen concentration we were using 0.256 mol per meter cubic, which is measured in a pure water. But actually, our experimental was done in a phosphate buffer solution, that is a salty solution. So from Henry's law, we know the oxygen solubility should be lower in a salty solution. So we corrected the value from 0.256 mol per meter cubic to 0.243 mol per meter cubic. Similarly, we had a look of the Stock-Einstein equation. Because of the greater dynamical viscosity of the salty solution, and also because of a lower temperature in our lab, which is 21 degrees, so the diffusion coefficient should be changed from 2 times 10 to minus 9 meters squared per second to 1.82 meters squared per second. After we did this, like a parameter correction, we run the simulation again. The newly added green line is an optimized simulated result to single microelectrode. As you can see, the maximum deviation has been decreased from around 18% to less than 2%. Now, we think this model is ready to be extended to a 3x3 model now. But before that, I'd like to share some results I got experimentally to tell you what actually diffusion overlapping looks like in an experiment. For easier comparing, we scaled down the current to microelectrode array, which is a 3x3 microelectrode array by a factor 9. So that is shown as a 1 nice eye array in blue. And the green line here shows the experimental result to a single microelectrode. As you can see, the current from 10 seconds of the blue line is lower than the green line, and it decreases with time increasing. This phenomenon does confirm that the diffusion overlapping exists in our microelectrode array, and it becomes more significant with time increasing. So we saw that in our experiment now, and we want to apply that in our model. The first step, we needed to do some alteration of our model. The weight of this simulation box should be changed from a semi-infinite length, which is 1,000 micrometers, to a half-inch patch length, that is 100 micrometer. Similarly, we needed to change the bulk boundary condition from the oxygen concentration to 0 flux because of the diffusion overlapping. After we did this alteration, we run the simulation again. The green line here showed an experimental result to microelectrode array, and the orange line here is a simulated result to our microelectrode array. It's very obvious that simulated results decrease much more rapidly than our experimental result. Why it could happen? So we think it may come from an assumption of the microelectrode array with infinite reacting interfaces. That means that actually we only have a 3x3, that is 9 microelectrodes in our array. That means we didn't account the effects caused by the corner and the edge microelectrodes. So from a literature, we find a way to do this geometry correction. The current to the microelectrode array with a finite element can be calculated by the current to the single isolated microelectrode and the current to microelectrode array with infinite elements. After this correction, we run the simulation again. The maximum deviation has been decreased from around 47% to less than 5%. Now we think our model is accurate enough to do this job now. So from this project, we built the numerical models for the single microelectrode and the 3x3 microelectrode array. We validated our models by comparing with our experimental results. From the minimum deviation, we confirmed our model can simulate the diffusion, oxygen diffusion patterns and diffusion overlapping effects accurately. So in the future, we'd like to use this model to refine the designs of our oxygen sensor. Especially, we are quite interested in the biofouling effects and then how to mitigation the biofouling effects on the oxygen sensor. So thank you very much for listening. Any questions?